You've probably heard it. You are made of stardust. It gets said at graduation speeches, printed on posters, used as a lyric in songs. It sounds beautiful, cosmic, like someone reaching for a metaphor to make you feel connected to something larger than yourself. It isn't a metaphor. It is a precise, specific, experimentally verified claim about the physical origin of every single atom in your body, the carbon in your DNA, the iron in your blood, the calcium in your bones, the oxygen moving through your lungs right now. Every atom, traced, verified, origin known. And the chain of evidence that proves it, from the first moments of the universe to the atoms currently making up your hand, is one of the most extraordinary stories in all of science. Not approximately, not poetically, literally, precisely, measurably true. Let's start at the beginning, the actual beginning, the Big Bang, 13.8 billion years ago. The universe begins as an extraordinarily hot, dense state and expands. In the first 3 minutes, when the universe is hot enough for nuclear fusion, matter forms, elements form, but not many. The Big Bang produced hydrogen, 1 proton, the simplest possible nucleus, and helium, 2 protons, 2 neutrons, and trace amounts of lithium, 3 protons. That's essentially it. The primordial universe was roughly 75% hydrogen and 25% helium by mass. Almost nothing else. No carbon, no oxygen, no iron, no calcium, no nitrogen, no phosphorus, none of the elements that make chemistry interesting, none of the elements that make biology possible, none of the elements that make you possible. The Big Bang built the raw material, hydrogen and helium. And hydrogen and helium by themselves make nothing complex. They make gas clouds. They make the simplest possible stars. They do not make life. They do not make planets with oceans and chemistry and organisms. Something had to build the heavier elements. That something is stars. A star is a balance, gravity pulling inward, the weight of an enormous mass of hydrogen pressing toward the center, and energy pushing outward, the energy released by nuclear fusion in the core. When the temperature and pressure at the center of a collapsing hydrogen cloud reach about 10 million degrees, hydrogen nuclei start fusing. 2 protons becoming helium-4, releasing energy. That energy provides the pressure that holds the star up against its own gravity. That balance, gravity in, fusion out, is a star. Our Sun has maintained that balance for 4.6 billion years. It will maintain it for another 5 billion. But fusion doesn't stop at helium. That's where it gets interesting. As a star burns through its hydrogen, the core contracts, temperature rises. At around 100 million degrees, helium nuclei start fusing. 3 helium nuclei, through a specific reaction called the triple alpha process, fuse into 1 carbon nucleus. Carbon, the backbone of all organic chemistry, made in stars. In more massive stars, stars 8 or more times the mass of the Sun, the process continues. Carbon fuses into neon, neon into oxygen, oxygen into silicon. Each stage requires higher temperature. Each stage produces heavier elements. In a massive star near the end of its life, there are concentric shells of burning, hydrogen burning in the outermost shell, helium inside that, then carbon, neon, oxygen, silicon. Each shell producing the fuel for the next inner shell. And at the center, iron. Iron is where it stops. And here's why that matters enormously. Every fusion reaction from hydrogen to iron releases energy. That energy is the star's support system. But iron is different. Iron 56 is the most stable nucleus in existence. Fusing iron doesn't release energy, it absorbs it. The moment a massive star builds an iron core large enough, roughly 1.4 times the mass of the Sun, fusion can no longer provide support. What happens in the next second is the most violent event in the universe short of the Big Bang itself. Gravity wins. The iron core, the size of Earth, collapses to the size of a city in less than a second. The density becomes so extreme that electrons and protons are forced to combine into neutrons. The core becomes a neutron star, matter so dense a teaspoon of it would weigh 1 billion tons. The collapse releases an enormous amount of energy, and the outer layers of the star, falling inward, hit the rebounding core and are blasted outward. A supernova. In the extraordinary conditions of that explosion, the temperatures, the neutron densities, the sheer energy, elements heavier than iron are forged. Gold, silver, platinum, uranium, iodine, all the elements beyond iron in the periodic table, made not in a star burning steadily, but in a star dying violently. The supernova releases more energy in a few seconds than the Sun will release in its entire 10 billion year lifetime. It's so bright it can outshine an entire galaxy, hundreds of billions of stars, for weeks. And it does something just as important as the energy release. It distributes. All those elements forged in the stellar interior, carbon, oxygen, iron, all of it, are locked inside the star while it's alive. The supernova is the distribution mechanism. It blasts the star's material into space at thousands of kilometers per second. That material drifts outward, cools, mixes with surrounding interstellar gas, forms clouds, nebulae, enriched with heavy elements that didn't exist before this star lived and died. Those clouds are pulled back together by gravity, new stars form, new planetary systems. Each generation of stars enriches the universe with more heavy elements than the last. Our Sun is a third-generation star, or later. It formed 4.6 billion years ago from a cloud of gas and dust that already contained the heavy element output of multiple previous stellar generations. Every heavy element in the solar system, in Earth, in you, came from stars that lived and died before the Sun existed. Now, how do we actually know this? Because this is the part that transforms it from a compelling story into verified science: spectroscopy. When light passes through a gas, specific wavelengths are absorbed, and each element absorbs a unique set of wavelengths, a fingerprint, as specific as a barcode, unique to each element. When astronomers analyze starlight, split it into its component wavelengths, they see these absorption lines. They read which elements are present in a star and in what quantities. We've done this for hundreds of thousands of stars, and the pattern is clear. Old stars, population 2 stars, formed early in the universe's history, have very low abundances of heavy elements. Iron, carbon, oxygen, present in tiny fractions. Young stars, like the Sun, formed later when multiple generations of supernovae had already enriched the interstellar medium, have much higher heavy element abundances. The heavy element content of the universe has been steadily increasing for 13 billion years as successive stellar generations live, produce elements, and die. We can trace the exact path. From Big Bang hydrogen, through stellar nucleosynthesis, through supernova explosions, into the interstellar medium, into the cloud that formed the solar system, into Earth's chemistry, into biology, into you. And we can be specific about which elements came from which processes. The oxygen you're breathing right now, made in massive stars, in the oxygen-burning shells of stars at least 8 times the mass of the Sun. Those stars lived for a few million years and died in supernovae that scattered their oxygen into space. The carbon in your DNA, made through the triple alpha process, 3 helium nuclei fusing into 1 carbon nucleus, in stars similar to or larger than the Sun. That specific reaction in stellar cores produced the carbon backbone of every organic molecule in your body. The iron in your hemoglobin, the iron that allows your red blood cells to carry oxygen, the iron that makes your blood red, forged in the silicon-burning core of a massive star and distributed in a supernova explosion. The iron in your blood was inside a dying star. The calcium in your bones, produced in stellar nucleosynthesis and supernova explosions. The nitrogen in the amino acids that build your proteins, stellar origin. The phosphorus in your DNA backbone, stellar origin. Every element in your body has a traceable origin, a specific type of star, a specific nuclear process, a specific mode of death. You are not vaguely connected to stars. You are assembled from the specific outputs of specific stellar processes. Identifiable processes, verifiable processes. Now think about a timeline. Big Bang, 13.8 billion years ago. First stars. Population 3 stars, massive, made entirely of hydrogen and helium, form roughly 100 to 200 million years later. They live for a few million years. They die in supernovae, enriching the universe with the first heavy elements it has ever contained. Second-generation stars form from that enriched material. They live. They make more heavy elements. They die. Third-generation stars, like our Sun, form 4.6 billion years ago, built from the accumulated debris of at least 2 previous stellar generations. The solar system's heavy elements, all the carbon, oxygen, iron, calcium, came from those previous generations. Earth forms from the same cloud. Chemistry happens. Simple molecules, complex molecules. The first self-replicating molecules. Life. Single cells. Multicellular organisms. 3.8 billion years of biological evolution, each generation building on the last. You arrive. The hydrogen in your cells, the hydrogen in the water that makes up most of your body, is as old as the universe. It was produced in the Big Bang 13.8 billion years ago. It has been part of nebulae, stars, interstellar gas, oceans, organisms. It has been through more transformations than any history could fully capture. The iron in your blood has been inside at least one star, possibly more. It was forged in a supernova, scattered into space, incorporated into the solar nebula, concentrated in Earth, dissolved in ancient oceans, incorporated into early biochemistry, and passed down through billions of years of evolution until it ended up in your hemoglobin. Now, you are made of stardust doesn't capture this. It's too gentle, too vague. You are the current address of atoms that have been through stellar interiors, supernova explosions, billions of years of interstellar drift, the formation of a solar system, the chemistry of a young planet's oceans, and 3.8 billion years of biological evolution. Every atom in your body has a history longer than the Earth. A history that includes violence, the death of massive stars, and transformation, the slow building of chemistry over geological time. The universe didn't produce you as an afterthought. It spent 9 billion years building the right elements, arranging them into a solar system, and then spent another 4.6 billion years running chemistry and biology until something emerged from that process. Something that could look back at the stars and recognize where it came from. That is not the same as being made of stardust in some vague cosmic sense. That is matter that has been through everything. Every stellar process, every nuclear reaction, every transformation, arranged into a configuration that can understand its own origin. The science proves the physical connection completely, every atom traceable, every process verifiable. The chain from Big Bang to your bloodstream is unbroken and documented. What science can't tell you, and I want to be honest about this, is what it means. The atoms don't care about their history. Carbon doesn't remember being inside a star. Iron doesn't know it was forged in a supernova. The atoms have no experience of their own journey. But you do. You, this specific arrangement of star-forged atoms, can trace the entire chain. You can look at a star and know you are made of what it's made of. You can understand the nuclear reactions that built you. You can hold the full 13.8 billion year history in your mind and know where you fit in it. Whether that's just physics, atoms arranged into a pattern complex enough to model its own origin, or whether there's something extraordinary about matter that can comprehend its own history, I don't know. But I think the question, asked with the full weight of the science behind it, is one of the most important questions you can ask. You are made of dead stars. And that's not a metaphor. That's the most extraordinary, literal truth about what you are.